Hi everybody. So this is an introductory video to the week 4-5 flip-flop virtual lab. So the lab is called Net Ionic Equations. Okay. The first thing I want to do is remind us about what happens when things dissolve in water. Okay. So if you remember, you probably talked about water being at least polar at some point in high school. Okay, and you probably looked at water a little bit, and you know the formula is H2O. Hopefully, you talked about at some point water looking something like a little bit of a Mickey Mouse of sorts. Okay, the ears. I'm going to try to draw this really tiny. Okay, the ears are H's, the hydrogens. So there's two H's. Those are those two guys right there, and then the O is that face of Mickey. If you're imagining it like a Mickey Mouse, the H's are the ears and the O is the face. So that's H2O. Okay, and I don't think you've talked about this just yet in your your lecture, but water's polar, and the reason why it's polar is the oxygen here has a stronger attraction to electrons than the hydrogens do. And we're not going to go into why that is, but just suffice it right now that the oxygen has greater attraction to the electrons than the hydrogens do, which means that the electrons spend more time around oxygen, giving oxygen, oops, misdrew that, a partial negative charge. Okay, the hydrogens then, so if the electrons spend more time around oxygen and give it a partial negative charge, that means the hydrogens are going to be partially positive because they have electrons hanging around them less often. So what happens is you have a polar molecule, you have one side that's partially negative and one side that's partially positive. Okay, what that does is it then starts pulling on anything else that is polar. It tries to pull things apart that are polar. Okay, and things that are soluble will dissolve in water because the attraction to water is greater than the attraction to whatever else it's with. Okay, so for instance, salt. Say we have NaCl. Okay, so Na is the smaller ion because he lost an electron, and chloride, is the larger ion because he gained an electron. Okay, and so what happens is these two guys, because one's positive, one's negative, they are attracted to each other. But water, especially when you combine multiple waters, actually has a stronger attraction to the ions than the ions do to each other. So what happens is a whole bunch of waters kind of gather around this chlorine and pull it apart. So you end up with the chlorine over here with several waters surrounding it. Looking something like that. Oop, you can't see all of it. There you go. So it looks something like that, where the chlorine ends up getting surrounded by several waters. Okay, the sodium is similarly going to be surrounded by waters. The difference in sodium is that because it's positive, the negative side of water is going to be attracted to it. And just so you know, the number of waters around each ion is somewhat dependent upon the size of the ion, as well as charge attractions and other things, but that's getting more advanced than we need. So in 2 dimensions, just for simplicity, we usually draw 4 waters around it, because that is reasonably accurate in 2 dimensions. Okay, but again, depending on the size of the ion, you might end up with more or less waters surrounding it in reality. Okay, so that's what happens when stuff dissolves. And again, if the water is more attractive, if multiple waters are more attractive to the ions than they are to each other, they'll get pulled apart and they will be soluble, they'll get dissolved. Okay, and again, when they get pulled apart, by the way, the word for that is dissociated. They will be dissociated because they get pulled apart because the waters have more attraction collectively than the ions do to each other. However, there are other ions that are so attracted to each other that water cannot really pull them apart. Okay, some other ions might be things like, say, silver, oops, having trouble writing here. Okay, we'll just rewrite. So silver, Ag, with chloride. Okay, I'm not going to get into in this video why these two are more attracted to each other, but silver and chloride have a greater force of attraction between themselves than sodium and chloride. So what happens is these two ions are more attracted to each other, and so they stick together more than sodium and chloride do, and so water cannot dissociate them as much. Therefore, they are more insoluble. This particular one is slightly soluble, but if we go up even more, there's say something like, say, lead, and let's go carbonate. That's what I was trying to come up with. So lead is a +2, carbonate's a -2, so they have bigger charges. Bigger charges means that they have greater attractive forces to each other, and so water cannot pull lead and carbonate apart. They stick together, and they are what we call insoluble. Okay, so there are salts that are soluble, and then will get dissociated because they have, compared to the collective attraction of water, they have less attraction between the ions, and so the water has more collective attraction, so it pulls them apart. Whereas there are some that are so attracted to each other that the collective attractiveness of water cannot pull them apart. Okay, so that's solubility. And that's going to come into play here in a little bit with net ionic equations. FYI, there is a table that tells us about solubility, okay, on the Moodle page. Okay, so there's this page here with solubility rules is available on the Moodle page. So just so you can see, let's see, here's chlorine right here, and here's sodium is in this row right here. So you look at sodium, you look at chloride, and it says S. S means soluble. Whereas you look at carbonate, CO3, and lead down here is I, insoluble, means it will not dissolve. Okay, so you can look at this chart to predict if something would be insoluble or not. Okay, so let's look at a demo and look at what's happening in that demo in order to figure out what is going on in the reaction, and then how would we write a correct chemical equation and then a net ionic equation from that. Okay, so first of all, I've got a beaker here, and I'm going to put silver nitrate in there, so AgNO3. Okay, I'm not going to show you on the solubility rules because I just showed them to you, but silver nitrate is soluble. Okay, so I'm going to put a couple of squirts of silver nitrate in here. Let me get one more. Okay, and again, the formula for this guy is AgNO3. Okay, if you look at it closely, you can see that it just looks like water. Okay, that's because the silver and the nitrate have been dissociated into the water, and the light just kind of, at least visible light, passes through the water unaffected by the silver ions and the nitrate ions in there, so it just looks like water, and the silver and the nitrate are just dissolved in there. Okay, I'm not sure how fast this is going to go, but we'll kind of see. I've got a piece of copper here. Okay, so it's copper wire that I've kind of bent into a little bit of a loop. Okay, and I'm going to drop this into the silver nitrate, and we're going to start watching the reaction while we start putting the equation together. Okay, so drop that in there. So I'm going to hold it up. Okay, initially we don't see much happening right off the bat. Okay, I can see some changes by eye that you probably can't see just yet with the camera. Okay, but I'm going to set this to the side, and then we'll come back to that. And actually, I'm going to add a little bit more silver nitrate to make sure that there's enough in there. I thought my wire would sit flat a little bit better. Apparently it did not. Okay, so again, we're going to set this aside. You can now kind of see that there's some floatiness going on in there, but we'll talk more about that in just a second. Okay, so I'm going to set this aside, and then we're going to start writing out a chemical equation. So if you remember, you should have covered chemical equations at least a little bit in like high school chemistry. So if you have an arrow in the middle, everything to the left of the arrow is what is present before the reaction, in other words, the reactants. Okay, so what did we have present before the reaction started? Well, we had the silver nitrate. Goodness, this shakes like crazy. This table's not very level. So we have AgNO3, and I didn't leave myself enough space. Okay, and the AgNO3 was dissolved in water. The state for that is aqueous, AQ. Okay, and into that I put copper solid, Cu little s. Those are the things that are present before the reaction starts. Okay, now we need to look at what is present after the reaction. Okay, and I'm actually going to shift. We'll leave it alone. Actually, no, I think I need to. All right, so we're going to shift, we're going to turn it sideways. Sorry if you have to turn your screen all of a sudden, but I need more space. Okay, so now we need to look at what is happening over here. Okay, you hopefully can see that there is little silvery gray stuff floating around in here now. Okay, go figure, that silvery gray stuff is in fact silver. Okay, it doesn't look too shiny in the camera, but if you actually look by eye pretty closely, I know you're not here, but I can actually see little glitter on the edges of the copper. Okay, it looks just kind of like gray moss in the video, but by eye you can actually see little glittering on there. Okay, so that's actually silver. And then the other thing you might notice is that there is a little bit of a blue tint to the water now. The blue tint in the water is the copper that has dissolved. Okay, so we end up with silver, Ag, and you can see that in here, the silver is pretty clearly little chunks. So that is now a solid. So we're getting silver solid. And then the leftover stuff, we have copper, which again is getting dissolved into the water with the NO3, the nitrate. The reason why we know that, again, I don't know how well you can see. I guess you can see it from that angle better, maybe. The water now has a blue tint to it. Okay, that's not really focusing very well. There we go. So the water has a blue tint to it, and that's characteristic of dissolved copper. So we're going to say that's CuNO3, 2. Okay, and again, if it's dissolved, the state would now be aqueous. And by the way, I know that there's a 2 here because copper can have a charge of a +1 or a +2. However, he's most commonly going to be a +2. And I know from experience that nitrate, it's going to be a +2 in the vast majority of cases. Okay, so on the lab sims, you don't have to come up with that. All the charges are fairly obvious, I think. So, but copper is usually a +2. All right, we do want to balance this, okay, just like we normally would on an equation. So I have 2 nitrates over here. In order to balance that, I need 2 nitrates on this side. I have to put a 2 in front of my silver. Okay, because I put a 2 in front of my silver here, I now have 2 Ags on this side. So I need to make sure I have 2 Ags here. So I put a 2 in front of my Ag there. And then you'll notice that there's 1 copper here and 1 copper here. So everything else is balanced. So we should be good. But, so this is the chemical equation. So this is the first thing that you need to do is write out your chemical equation. But then the net ionic equation is a little bit different than this. Okay, the net ionic equation is going to be a simplified version of this. Okay, and so what we want to do first of all is show everything as it actually exists before and after. So we put aqueous on this guy, but remember, we just showed you when stuff dissolves in water, when it's aqueous, it's not all together as one formula. It actually splits into two formulas. Okay, so in reality, the water splits up the Ag and the NO3 into Ag plus and NO3 minus. Okay, both of these guys need states that are aqueous. And notice we also include the charge on both of those. Okay, as soon as we split it up, the Ag isn't Ag like with no charge on it. It's actually the silver ion in this compound, and the water pulls it apart from the nitrate. So all we've shown is that in reality, like in this bottle over here, it says AgNO3 on it, but in reality, the Ag and the NO3 have been split apart by the water because it's dissolved. Okay, so that's all we've done here. Notice we do have a 2 on the front. So if we split two AgNO3s, we have two Ags and two NO3s. Okay. We also have a copper solid, so we're going to carry the copper solid straight down. Okay, and the reason why we carry the copper solid straight down is he doesn't get split up by water. So for the net ionic equation, really the only thing that changes is the aqueous stuff. Okay, so the copper solid is unchanged by this because he doesn't get split up. He just exists as copper solid. Same thing for our silver solid over here. It's unaffected by this change because he's a solid. Again, gases and liquids, same thing. If they're solid, gas, and liquid, do not change them for a net ionic because they're not split up in any way. However, over here we have another aqueous thing. So the water, again, is going to split up the copper and the nitrate. And again, I mentioned, and this blue is getting more and more intense. I can't see it really well still on the video, but this water in here is indeed blue. Okay, and that blue water means that it's got copper in it. Okay, so that means the copper has been dissolved by the water. And so the copper is now separate. As I mentioned, he's usually a +2 in a compound. Okay, and then the NO3 is also separate, but notice there are 2 of them. Okay, so we grab 2 NO3s. They're aqueous. Okay, so notice all we did here is we just took our 2 aqueous things and we split them up into charged ions. That's all we did. So nothing complicated there. The last step here is to recognize that this arrow here is essentially an equal sign. Okay, that means everything that is present before the reaction must also be present after the reaction somewhere. Okay, so because we cannot create or destroy matter. Okay, so we have 2 Ags, we still have 2 Ags, we have 2 NO3s, we have 2 NO3s, we have 1 Cu, we have 1 Cu, and if you look at the charge, I have 2 +1s over here for a total of +2. I have a +2 here. I have 2 -1s, and I have 2 -1s. So even our charge is balanced across. So this arrow is essentially an equal sign in mathematics. So everything on the left should be equal to what's on the right, even if it's rearranged. Okay? So the other thing you might remember from mathematics is if there is something that is the exact same on both sides of an equal sign, you can cancel it out. For instance, let's say we had maybe y plus x equals 3 plus x. There's an x that is in the exact same situation on both sides of this arrow, so we could eliminate the x because they're equal on both sides. Okay, in which case you get y equals 3. Okay, so hopefully that's kind of Algebra 1-esque stuff, so that shouldn't be too complicated. The same thing is true in chemistry, though. So notice I have 2 NO3s over here that are aqueous, and they're separated by the water. I have 2 NO3s over here that are aqueous, that are separated by the water, and they have the same charge. They are exactly the same on the left and on the right side of the arrow. Okay, so in our net ionic, we can actually eliminate these two guys. Okay, we call these spectator ions. Okay, spectator ions because they did not change or even participate in the reaction. They were present in order to get the silver and the copper there, okay, but they didn't do anything. The NO3s were floating in the water before the reaction. They were still floating in the water after the reaction. They did nothing in the reaction except spectate or stand by and watch the reaction going on. Okay, so we're now going to rewrite this equation minus the things we just eliminated. Okay, so I eliminated the NO3s, but I still have 2 Ag, so I'm going to rewrite 2 Ag plus aqueous plus Cu solid gives us 2 Ag solid plus Cu plus 2 aqueous, and then we've got our eliminated NO3 on the side. Okay, so hopefully that kind of makes sense for how to generate a net ionic equation. Okay, I'm going to make a second video with a second example in case you feel like you want it, but this is essentially what you're trying to produce for the week 5 net ionic equation lab. All right, have a great one, y'all. Enjoy your virtual lab experience for week 5.